NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How's everyone tonight? Good. Yeah, that's what we like to hear. Well, thanks for coming out to join us again for our inaugural 2015 lecture. So as NASA plans ambitious new robotic missions to Mars, the spacecraft needed to land safely on the planet's surface necessarily becomes increasingly massive, hauling larger payloads to accommodate extended stays on the Martian surface. The heavier planetary landers of tomorrow, however, will require much larger drag devices than any now in use to slow them down. And those next-generation drag devices will need to be deployed at higher supersonic speeds to safely land vehicle, cargo, and crew. NASA's Low-Density Supersonic Decelerator, or LDSD, technology demonstration mission, led by the Jet Propulsion Laboratory, has conducted full-scale stratospheric tests of these breakthrough technologies high above Earth to prove their value for future missions to Mars. Tonight, we have two guests to explain how this stuff works. Mark Adler is the project manager of the Low-Density Supersonic Decelerator project and is a JPL engineering fellow. He has worked at JPL for 23 years on many assignments, including the Cassini-Huygens Program Lead Mission Engineer, the Mars Exploration Program Architect, Mars Sample Return Chief Engineer, Mars Exploration Rover Mission Manager, Mars Sample Return Pre-Project Manager, and is the JPL Chief Mission Architect and Manager for Advanced Concepts. He received his PhD in physics from Caltech and both his MS in electrical engineering and his BA in mathematics from the University of Florida. He's also happy to see that Florida has a new football coach. Ian Clark is the principal investigator of the LDSD project. He has been a systems engineer at JPL for 5 years. He holds BS, MS, and PhD degrees in engineering from the Georgia Institute of Technology, where he also previously served as a visiting assistant professor and managed the Entry, Descent, and Landing Research Group. Ian grew up in Tallahassee, so he's very happy to see that FSU has beaten Florida for the past 5 years in football, and this year in basketball too. Ladies and gentlemen, that's why I love this job. Ladies and gentlemen, please help me welcome tonight's guests, Dr. Mark Adler and Dr. Ian Clark.
Thank you. Go Knowles. Thank you all very much for coming. So the title of our talk is Low-Density Supersonic Decelerators, and really we're going to do a couple things. We're going to tell you what those are, but before I do that, I want to talk about why it's hard to land things on the surface of Mars. The subtitle is Towards the Next 40 Years of Landing on Mars. Before I tell you how we're going to use the next 40 years, I'm going to give you a little bit of history about what the previous 40 years of landing on Mars looked like and how we got to where we are today. Then I'm going to describe some of the technologies that this project is developing. And then Mark's going to come on stage and talk about some of the pretty exciting tests that we're doing to help understand those technologies and help develop them for the next 40 years. It should be. Is this on? There we go. We can land on Mars, but power buttons. Good grief. So this is the Curiosity rover. Hopefully a few of you guys remember that a few years ago we landed this on the surface of Mars. This is a 1-ton nuclear-powered, laser-equipped, 6-wheel drive rover, and it is the largest, most massive thing that we have ever landed on the surface of Mars. Putting it safely there was a massive technological undertaking, and you're going to hear a little bit about why that was. But before I do, actually I'll point out, this is operating on Mars today. In fact, if I go back one slide, I've got this orbital picture right here is Mount Sharp, and at this very moment, Curiosity is climbing up Mount Sharp and doing amazing science for us. How did we get this on the surface of Mars? Oops. Well, we start at the top of the atmosphere. We're going 10,000 miles an hour, and we're using a very large 4.5 meter, over 15-foot diameter aeroshell to slow us down. That aeroshell can take us from the top of the atmosphere going 10,000 miles an hour and get us down to a speed of only about 1,000 miles an hour. It's very thin atmosphere. Once we get 1,000 miles an hour, that's not slow enough, so we have to hit the emergency brake. We deploy a 60-foot parachute at over twice the speed of sound. That slows us down from 1,000 miles an hour down to about 200 miles an hour. Still pretty fast to be hitting the surface. So we have to turn on our rocket engines. We ignite our sky crane. We turn on the rocket engines. The rockets slow us down from about 200 miles an hour down to about 1 mile an hour, get us close to the surface, and it gently lowers the rover. The mobility system, the wheels deploy on the rover. We gently put it down at a few centimeters per second. We cut the tethers. That sky crane flies away in the distance. And now we have the rover there on the surface of Mars today, where it's doing amazing science for us. If we look at the state of the art and the technologies necessary to do that, MSL is the cutting edge. Again, at the top of the atmosphere, we started with an enormous aeroshell, 15 feet in diameter, the largest aeroshell we've ever used in another planet, and in fact, the largest aeroshell, or nearly the largest aeroshell that we can fit on any launch vehicle that we have in our inventory or that we have available today. We have a 60-foot supersonic parachute. This is the largest parachute ever used at Mars and ever tested at multiple times the speed of sound. It's the largest parachute we can use today. This is the state-of-the-art in the technology. And then on the landing system, the sky crane system is the state-of-the-art in technology. We've used airbags in the past. We've used rockets. The sky crane was by far the most technologically advanced. Actually, I had somebody point out that is not in a. I know black turtleneck, blue jeans looks like Steve Jobs. It's not. This is some support personnel helping us out with some of our parachute testing. So we've gotten pretty good at landing things on the surface of Mars. We've been able to grow our payloads. If you remember, about 20 years ago, we landed the Sojourner rover, Mars Pathfinder. This is about a microwave-sized rover. It weighs about 25, 30 pounds or so, relatively small. And we were able to grow that up towards the Mars exploration rovers. Those were about 350, 400 pounds or so. The Phoenix Mars lander, about 800, 900 pounds. And most recently, of course, the Mars Science Laboratory, nearly 2,000 pounds in mass. As we've been doing this, we've uncovered one of the phenomenon associated with landing on Mars. We call it the square cube law. That is, as our capsules get bigger, the area of the capsule, the ability to create drag, to slow the capsule down, goes up with the square of the diameter. But the volume is going up with the cube of the diameter. We're incredibly efficient at cramming lots of stuff in whatever volume we have available. That means that the mass is going up with the cube of diameter. Because the mass is increasing faster than the ability to slow it down, the drag that we're producing, that means it gets more and more difficult to slow down these larger and larger payloads. Eventually, we want to be able to land this 2-story condominium on the surface of Mars, something very large, very massive. And so once you get to those, you're well beyond the regime of anything that we've done today, and we're well beyond the regime of what we can do based on the Curiosity experience that we've had. This isn't something entirely new. We've actually been in this situation before. So let's go back to 1962. NASA's starting to build giant rockets. We're starting to think about landing on the surface of the moon. And we come up with an idea for a program called Mars Voyager. This isn't the Voyager program that we would eventually send a spacecraft out to the outer planets and even beyond our solar system, or actually there's a prototype model of it right here to get a feel for that. This was a predecessor to that we called Mars Voyager. At this time, NASA's developing big rockets. We knew that we were developing the Saturn V rocket, the largest rocket ever built, ever developed, ever flown, and the rocket that we use to put humans on the surface of the moon. NASA wanted to be able to use that rocket to send a payload to Mars. We hadn't ever landed anything on Mars at the time. We knew very little about Mars, particularly the Martian atmosphere, so it was a tremendous undertaking, an extremely bold mission. And it was in the development of this project that we started learning about how difficult it was going to be to land on the surface of Mars. A lot of that difficulty stems from the Martian atmosphere. If you think back, I told you we like to use drag to slow down. There's 4 components to how you generate drag: how fast you're going, how big you are, the drag coefficient, a measure of the efficiency of your ability to produce drag, and the density of the fluid in which you're moving through, or the density of the atmosphere. Prior to 1964, we had never visited Mars. We had telescopic observations. We were able to study the atmosphere from afar, try to get some estimates as to how thick the Martian atmosphere was. We knew that it had an atmosphere, and we knew that it was thinner than Earth's atmosphere, but we didn't know by how much. Our best guesses were about 10% the thickness of Earth's atmosphere. It wasn't until we started doing the Mariner program that we got our first flyby of Mars. This was in 1964, that we were able to fly by very quickly and do a sounding and sample or get an idea of how thick the Martian atmosphere was. And even that told us it wasn't 10%, it was something even smaller than that. Only data chart I have, so I apologize. This is the altitude on Mars, and this is density. And you notice the scale down here is on powers of 10. That means that each successive movement to the left is 1/10 the previous amount. And this chart doesn't even have Earth on it. I had to add that down here. So here's Earth sea level density. And prior to 1964, we thought Mars was maybe about here. Then we did a flyby. We realized it was about half of what we thought in 1964. But we still had tremendous uncertainty. Up here, the altitudes where we'll be slowing down, it was plus or minus 2 orders of magnitude. 1/100th. It could be 1% or 1/100th of a percent. We just did not know. Then in 1967, we had another Mariner flyby. We started learning just how thin that atmosphere was, and it dropped another order of magnitude, even thinner than we thought. This meant that we were going to be slowing down that 12-ton Mars Voyager payload. We needed to have something very big to be able to react against the atmosphere. In that vacuum, we started thinking of all sorts of things. One of the first things we thought of, well, we've got these parachute devices. They've been working very well to save people as they jump off of buildings or out the back of airplanes. They seem to have worked very well for those kinds of conditions. Can we use them at the speeds and in the atmosphere environments that they would see at Mars? So we started doing some testing associated with that. We also started developing inflatable drag devices, things that we could attach to the entry capsule itself, things that would inflate and expand and increase the size of the entry capsule to create more drag to help slow it down through that very tenuous, very thin atmosphere. So you see some images associated with that. You've got some videos of some of those very early parachute tests where we took rockets and we took them to altitude with balloons and we got them going several times the speed of sound, and we would shoot a parachute out and see what did it do in that sort of environment, going several times the speed of sound in a very thin atmosphere. We got wind tunnel testing of devices that were about 5 feet tall, but we could deploy these things at 4 times the speed of sound in a wind tunnel and see how they inflated. And in fact, these guys even had little scoops on the side to ingest the air and help pressurize. They were ram air inflated. We did some more testing and even some low altitude drop tests. We started learning much more about these devices. We started learning how efficient they were, how big they could be, what the materials that we would have to use to build them, and we started pushing the envelope even further. On the parachute side, we started testing at higher and higher Mach numbers. The video on the left is Mach 3. You see how crazily dynamic the parachute is. It inflates, it expands, it contracts, it's oscillating all over the place. The vehicle with the camera on it's dancing all over the place. But eventually, it does slow down and it stabilizes and it produces an awful lot of drag for a device that's actually very lightweight. And this one was deployed at about 3 times the speed of sound. This worked reasonably well. We understood the violent oscillations, but the material, the fabric, in this case it's just polyester, survived. And so we wanted to go further. So we tried going, well, let's try 3.3 times the speed of sound, just 10% faster. And here's another video, and we started learning, you know what, these have limitations. The violent oscillations associated with them were too large. The heating associated on those Mach numbers was too high for these materials to withstand. So we started learning that parachutes do have their limits. Also, the drag produced, well, other than the fact that it has holes in it, the drag produced by this device is not particularly good at those high Mach numbers. But some of the other devices that we were testing, like these guys here, were very efficient at higher Mach numbers. Mach 3, Mach 4, they produced very good drag. But at the lower end, subsonic, Mach numbers less than 1, they were not as efficient. So we started learning, you know what, parachutes maybe have a regime in which they're very useful, and these attached inflatable devices maybe have a regime in which they're very useful. Oops, get through that. And that was all for the Mars Voyager program. Eventually, that program would go away. It was too bold, too ambitious, too expensive for NASA at the time. We were still trying to do Apollo, and it was down-selected in favor of the Mars Viking program. Those would be the twin landers, the first things that we ever landed on another planet, Viking 1 and Viking 2 that we landed in 1976. Viking was a much smaller spacecraft. We understood a lot more about the Martian atmosphere by that point. We understood that we didn't need some of these larger inflatable drag devices, that parachutes were going to be adequate enough. And that became the de facto standard for how we landed things on Mars. The parachutes that came out of that testing were the same parachutes used for Viking 1 and Viking 2, and the same parachute design that we've used on every Mars mission since. That includes the Pathfinder missions, Phoenix, the Mars exploration rovers, the most recently, the Curiosity rover, and even the Huygens spacecraft that landed on Titan used the same basic parachute design that came out of the 1960s testing. On the side of the attached inflatable devices, those found technology uses in other areas as well. We use them for stabilization on the Gemini ejection seats, meteorological sounding rockets that we'd send to nearly the edge of space to help understand the atmosphere at those altitudes, decelerators for munitions. But all of the testing that occurred in that 60s and 70s largely went away. We had the technology base to do the things that we wanted to do until recently. And we started spinning back up, you know what? We want to start understanding these devices a little bit more as we want to start trying to land larger things on the surface of Mars. And so it's the future that's really motivating this project. And the future looks something like this. We want to be able to land things bigger than Curiosity rover, more capable, more exciting. We want to land missions to be able to return samples from the surface of Mars and bring them back here to Earth so that we can study them in much, much greater detail. We want to be able to land things like greenhouses on the surface of Mars to see if we can grow plants using the Martian sunlight, but otherwise maybe providing some of the materials necessary for those plants to survive. We want to be able to perhaps land small factories to see if we can take the carbon dioxide atmosphere and create rocket fuel from that. And eventually, as we cast our eyes to the horizon, we want to be able to land humans on the surface of Mars. And that means all of the things necessary for humans to survive. There's not exactly a bunch of Martian caribou that we can go hunt and live off of. It's basically you have to bring everything that you need to survive when you get to Mars. That means the habitats, that means the mobility systems, the food, the water, the resources, the iPads, iPhones, whatever it takes for the astronauts to survive for days, weeks, months on end. And that means all of the mass associated with that. So enter the Low-Density Supersonic Decelerator project. We've gone back to the recognition that we need larger drag devices to be able to slow down these increasingly larger payloads on the surface of Mars. We need these large drag devices to create the drag in this very, very thin atmosphere. So LDSD is developing 3 new decelerator technologies. 2 of these are a flavor that we call Supersonic Inflatable Aerodynamic Decelerators, or SIADs. NASA loves its acronyms, and so just about everything that you see on here has an acronym associated with it. So the first one, the one in the top left, is a 20-foot diameter inflated donut, something that we can deploy at 4 times the speed of sound and slow a modestly sized, something maybe 50 to 100% larger than Curiosity, down to conditions where we can use a parachute. We're developing a 26-foot diameter device, something, the top one we call SIAD-R, Supersonic Inflatable Aerodynamic Decelerator, -R, and the R stands for robotic missions, because those would be targeted for more near-term robotic missions. The one on the bottom is called SIAD-E, and the E stands for exploration. These would be human precursor kind of missions. But to go along with that, because we know these devices work very well for Mach 4, but not so great subsonically, we're developing a new parachute, an enormous parachute, twice the area of any parachute that's ever been used on Mars. It's 100 feet in diameter. It's the size of a small warehouse. And we're also trying to push the envelope of the Mach numbers that we can use these devices. So we're going from the Mach 2 qualification that we have for our parachutes today up to about 2.5 or so. So a little bit of details on that. I mentioned SIAD-R. It's an inflated donut. Keep in mind, nobody has done anything to this scale and at these conditions before. These are the first steps, the first forays, and what it means to develop technologies, inflatable devices that would be used on Mars. When we took those first steps, we wanted to jump from something that we understood. We started with a device that's modestly small, 20 feet in diameter, and we knew things. We wanted to make this thing not necessarily a lot of pressure to inflate it. We needed to be able to get that thing inflated very quickly. As your capsule's screaming through the atmosphere, if it takes a long time to inflate the device, then you can start disturbing the capsule. You can get half of it inflated and maybe not the other half, and the capsule can start to tumble. The other thing that we wanted was to make the device as rigid as possible, because that's what we understood. And there's a lot of nice things about having rigid devices. Primarily, the shape is known. If we know the shape, that means it's a lot easier to analyze it. It means we can do things like, let's see, I've got one in my pocket here, that we can take little models like this. We can shoot them out of a cannon. We can watch how they fly. We can take pictures of them as they fly. And we can back out what the aerodynamics of this device are in conditions very similar to what they would see at Mars. And then we can take those aerodynamics and we can scale them up. And we can feel comfortable that the way that little model flew is the same way that a 20-foot diameter device would fly at Mars. It also means that the qualification is much simpler. The structural aspects of it. You can take it, inflate it, and because you know the geometry, you know how to apply all the different loads and environments to it. So that's what we started with here, something that we could inflate very quickly. In fact, the inflation pressure on this guy is only about 3.5 pounds per square inch, not a whole lot. The volume is relatively small, and we've even been able, for this device, to use off-the-shelf automotive gas generators. Think about the things that are behind your steering wheel to inflate your airbag in the event that you're in an accident. We actually have 18 of those that we use to inflate this in a fraction of a second. You'll see videos of that in a moment, a little bit later. The second device, I just spent a while explaining why we like nice, rigid, rapidly inflating devices. This is at the other end of the spectrum. And so, sure, we would like for our inflatable devices to be rigid, but as they get bigger, and they will need to get bigger as we want to land bigger and bigger things, you have to give up on that. At some point, the shape becomes flexible. The geometry it takes is going to be a function of the way the air is moving around it, and the way the air is moving around it is going to be a function of the geometry it takes. So that coupling is something you're going to have to understand, or we're going to have to understand, as we want to land bigger and bigger things on Mars. This device starts to do that. It's something very flexible, but it's also ram air inflated. It's very similar to devices that were tested, and you saw these images from before, back in the 1960s, but now we're taking it to the scales that would be necessary to use it at Mars. So it's 26 feet in diameter. Here's a prototype that you see being inflated. These are the ram air inlets that we use to scoop up the air and help pressurize this device as it's inflated. Here's the engineer responsible for delivering that. And then at the top, we had to get creative with how we inflated it because we didn't have an air, a Mach 4 wind to inflate this thing in. So we took 27 bounce house blowers and we supercharged them together. And we plugged them into the inlets to get it up to about half a PSI. Very small amount of pressure, but even that little bit of pressure is enough to get this thing up to shape and would be enough to have this thing produce an enormous amount of drag if it were at Mars. It's something that we didn't have to start from the very beginning from scratch on because of all that testing that occurred. It was all mostly subsonic testing, wind tunnel testing, small scale supersonic testing, but also even large devices that were dropped from the helicopter in 1965. And this is I think about 13 meter, 30 foot diameter model or so. So we had some heritage that we could draw from as we wanted to develop this device. But we have to develop something else. We need that subsonic decelerator. So we're building a new parachute to go along with it. I mentioned already it's an enormous parachute. It's 100 feet in diameter, twice the area of anything that we've ever used at Mars in the past. It's also a new parachute design. We've been using the same parachute design for 40 years. We've learned a lot about parachutes in those 40 years, and we've learned that there are more efficient designs, and so we're starting to leverage some of that knowledge and apply it, and now we're starting to develop parachutes of more efficient designs that we can use supersonically. To get a feel for the scale, there's the Phoenix parachute down here, the Viking from 1970s, most recently the Mars Science Laboratory or Curiosity rover parachute, and here's the LDSD parachute with the LDSD entry vehicle. That overall, the scale you get a feel is the size of a 747 jumbo jet. Very, very large scales, but again, because the atmosphere is so thin, that's what's necessary. All of these devices are flexible. They're all made from very flexible materials. Our parachutes are made from nylon, like this. Very lightweight. Maybe this is something like what your camping tent would be made out of, but also very strong. About a 1-inch wide strip of this would support a pretty hefty bag of dog food, but it also has downsides. If it develops a tear like this, I can go all sorts of Hulkamania and rip right through it. So nylon in and of itself isn't good enough. We couple it with other materials like Kevlar or material very similar to Kevlar. I've got more pockets. Yeah. I should have wore cargo pants. I could have brought more toys. So the suspension lines, the ropes that connect the parachute to the test vehicle are made from a material called Technora. This is a very thin piece of rope that would support over 2,000 pounds. So I could lift up a 2,000 pound, well, not with these guns, I couldn't. Somebody could lift up Curiosity with just this single piece of rope. The inflatable drag devices, that 6 meter or 20 foot diameter donut, that's made from Kevlar 29, the same Kevlar that's used in bulletproof vests. In fact, when we started this project, we had a hard time getting Kevlar 29. It was during the surge in Afghanistan, and all the Kevlar 29 in the country was being used to develop bulletproof vests for the soldiers. Eventually, some became free, and we were able to use that to build our devices. But also, that means we need sewing machines, and lots of sewing machines. All of these are stitched together. The image that you see on the left here is we had to order special sewing machines, one with 4 needles that we could use to help fabricate and put together the parachute. Earlier this week, I was at one of the fabrication facilities in Mississippi, and they had an 8-needle sewing machine that was probably built in the 1930s or 1940s, but it's still very useful and still something that's required to build these devices that, again, we're going to be using on Mars. I'm not sure if Isaac Singer or Elias Howe knew 150 years ago that their inventions were going to be critical for putting humans on the surface of Mars, but that's where we are today. So those are the devices, those are the materials, and that's the history. Mark's going to come up here and talk to you a little bit about some of the exciting testing that we have to do to make sure these devices work.
Okay, so first, I'm sure you've been dying to know about the politics, so I'll spend just a minute on that. We started about 4 years ago as a part of the new space technology program. Now, you all think of NASA. NASA is developing new capabilities. They are about technology. But surprisingly, NASA did not have, until about 4 years ago, a chunk of budget dedicated to just developing technology. But then they created this space technology program. It's called the Space Technology Mission Directorate. And LDSD was one of several projects that was one of the first ones started as part of that. And you can see in the background of the pictures there a whole bunch of other technologies that are being developed. They're about a $600 million a year program. We're maybe 40 million of that. So there's a lot of other programs going on to develop technologies in propulsion, in communications, and in many other areas to advance our capabilities in space. And we're one of those projects. So it's really, as Ian was mentioning, all about the testing. How do we test these things? You can build the devices. You can build, get your sewing machines and your fabric and put the things together, test them out, do some basic, pull tests on the things and make sure that they're strong enough locally. But to really test the devices, you've got to put them in the conditions that they're going to see at Mars. But we can't afford to send them to Mars to do that. We have to test them here at Earth. And so to test them here at Earth, we have several different venues that I'm going to talk about, including rocket sleds on the ground, wind tunnels, tests up at high altitude at Earth, in order to simulate both the thickness of the atmosphere in some cases and the strength of the wind that the devices are going to have to survive. And these tests have been quite an effort on the part of NASA, and we're working here at JPL on them. We're leading the project here at JPL. We have the Wallops Flight Facility in Virginia that's providing us a tremendous amount of support on the electronics and on the balloon services and on the launch services. As we use the China Lake Rocket Sled Facility, about 2.5 hours north of here, is this rocket sled track that we use as part of the Naval Air Weapons Station up there. And we use the Pacific Missile Range Facility in Kauai for doing some of these launches. So I'll go through and talk about some of those things. So here we are, we're testing the SIAD. The SIAD is built by the ILC Dover. We have some folk from ILC Dover here in the audience. I don't know where you guys are. Oh, there you are. Hi. And they're busy installing a SIAD on the vehicle today. And so what we do here is we put this thing on a rocket sled track. This track is a 4-mile-long railroad track. It's a standard gauge railroad track on which is attached these large metal structures. We have here a 25-foot tall, 50-ton steel structure on which we mount a test vehicle that our SIAD is inflated on. And back here are several Nike rockets. These are surplus rockets that were used originally on missiles that helped defend Los Angeles from Russian bombers. And that they were surplus, so there's a big vault of these things, and we get to use the rockets actually for free. And these rockets accelerate this thing down the track at about 300 miles an hour so that we can test the vehicles. So let me show you a video of that. So this is the vehicle on the track. You can see the rockets back here, the test vehicle where the thing is inflated. Here are cameras. We have several high-speed, high-resolution cameras that watch the inflation of the vehicle very carefully. Here it is rocketing down the track, accelerating to about 350 miles an hour. You can see you're heading down pretty fast. Unfortunately, nobody gets to ride on it. I wanted to get a seat, but they wouldn't let me. Here we have the vehicle in the wind. Now you see that this is a slow motion, so this thing inflates in less than half a second. So in very slow motion, you see it come out, become very rigid, just like Ian wanted. He wanted to see how rigid this thing would be. It came out and inflated. Once it completed the inflation, this thing was solid as a rock and deflected less than about a centimeter in that 250-mile-an-hour wind that it was going through. So it proved out our ability to operate the device, to deploy it from the stowed position, and to survive the winds, the high-speed winds here on the surface of Earth. And this simulates the dynamic pressure. We simulate the density times the velocity squared times the coefficient of drag to get the conditions that it would see actually at Mars with these rocket motors. We do a lot of testing in wind tunnels. This is the NFAC wind tunnel. It is the largest wind tunnel in the world. It is at Ames Research Center in Northern California. This wind tunnel, however, is not really big enough to test our parachutes. So these parachutes here, which look pretty big, are actually 1/3 scale. These are 1/3 the size of our actual parachute that I'll show you some other pictures of us testing. So we needed to subscale the parachutes to do this testing in the biggest wind tunnel in the world, which is why we have to develop these other test capabilities. And this allowed us to test the ability of these parachutes to be stable in the environment of the wind, to see what their drag is in the wind. We basically attach them to a big tower, deploy them in the wind tunnel, and see how they float around. I'll show you a video of that. We tested 55 different parachute configurations in this test. One of the ways we changed the configurations is we didn't make 55 parachutes, we made fewer than that. But between tests, we cut out pieces of the parachute with scissors to test a different parachute configuration. See the guys on the floor, they were cutting parachutes with the scissors. So we went through a lot of tests to see how they would behave with various amounts of porosity, how many holes we have in the parachute. And we learned a lot about what kind of parachute we wanted to fly. So here's an example of one of those tests. You see two guys standing over here, so you get a feel of the scale of the wind tunnel and get a feel for the scale of the test. We also had some smoke in some of the tests coming out of here to show the flow of the air around it. Even this small parachute is kind of starting to bang up against the wall. As you can imagine, a parachute 3 times as big would almost fill the wind tunnel, which is why we simply cannot use the wind tunnel for these tests. So here we're doing a test out at the Mesa at JPL. It's really just up the hill over here. And this is a 300-foot crane that we use to carry to hold up a rope that would be pulled up at high speed. This is being pulled up at about 120 miles an hour to show that we can actually strip the parachute out of the bag properly. This test went beautifully. We did this test a couple times, and it showed that we knew how to deploy the parachute out of the bag and that it could come out cleanly along with the suspension lines. Here's some other subscale testing. This is actually an even smaller parachute. This is a 5-foot diameter parachute, but that's the size we need to fit into this wind tunnel at Langley Research Center, which is another one of our partners. And at Langley Research Center, we're able to test at Mach 0.5 and Mach 0.1 the subsonic characteristics of these parachutes at low density. We can actually pump this tunnel down to have very thin air similar to Mars, and to see how stable the parachutes are and what their drag is at these low speeds, which again helps us with the configuration. In this case, helped us to compare the parachute configuration that we've been using at Mars up to now, the disk gap band, to the ring cell parachute, which is the new configuration we're using now. So as I mentioned, we have this problem with wind tunnels. The wind tunnels on Earth aren't big enough to test our parachutes. We basically had to create our own outdoor wind tunnel. And again, we went to this rocket sled track here at China Lake. And so on here you see this tripod. It's a white tripod that has a big pulley in it that a rope goes through. A rope comes straight down through the pulley, and then the rope attaches to this rocket sled. There's the rocket sticking up right over there. And so I'll show you how this all works. It's really very simple. We start with a helicopter. This is a Seahawk helicopter. It's basically the Navy version of the Black Hawk. Here's the parachute, which is held in its little can here until the helicopter picks it up with a rope. This is about a 4,000-foot long rope. And then we drop the parachute from the helicopter once it's at altitude. The helicopter then flies away once it's gotten rid of the parachute. The parachute then inflates as this 3,000-pound rope is pulling it down. So we wait for the parachute to stabilize. It stabilizes. And as the parachute is coming down, the rope is being sucked up into this thing here. We see this bullet come into the tripod, and that's when the rockets fire. And so the rockets fire and pull with 100,000 pounds of force on this rope to pull this parachute down. With 100,000 pounds is what we need to test the parachute. There's the guys operating it in the booth there. This is one of the first times we actually did it with the full-up configuration. And there's the parachute finally coming down. If you see right here, there's actually a hole in the parachute. This was exactly what we wanted to see. We wanted to know where the parachute would fail and when, and this told us what we had to strengthen on the parachute before we put it on more expensive tests. So that was a fantastically successful test. And then we have the standard kind of JPL high five, you know, So we did this test. We went up to China Lake, and we thought of this test. We thought, geez, this is a crazy test. You know, we want the guys in the helicopter to go up there and hold a parachute with a rope attached to a bunch of rockets and let go of it, and you know, pretty wild. So we go up to China Lake to talk to the guys, and so we have their chief safety guy and their chief pilot there, and we said, okay, so what we want to do is we want to carry it up with the helicopter and let it go and pull on it with the rope. You know, we're afraid, you know, these guys are going to go, oh my gosh, this doesn't sound safe at all. And they're listening to this whole thing, and they're going, yeah, we can do that. Sure. And so I concluded at that point that we weren't thinking crazy enough. So I went back to the guys and said, you know, you got You got to start thinking crazier. But of course, in China Lake, these guys deal with weapons. They figure nobody's shooting at us, right? So how bad could it be? So now we come to the big kahuna test. So to really test these things, we have to get them both to the thin atmosphere and to the high speeds that we need to test these devices. And so in order to do that cheaply, we use a technique that's actually similar to what was used to test the Viking parachutes back in the early 70s. We originally were looking at, well, can we just have a rocket to launch these things up to altitude and get them going? And that turned out to be way too expensive. We wanted to do this project in a very cost-effective way. NASA didn't have an infinite amount of money for these things. And so the most cost-effective way is to use actually a helium balloon. So we have a scientific helium balloon. These balloons are very large. It's a 34 million cubic foot balloon at altitude. And they're normally used to carry telescopes up to altitude. So NASA does a lot of experiments putting telescopes up at high altitude so they can see through very thin air. And so we use these same balloons from the Columbia Scientific Balloon Facility, which is in Palestine, Texas. And they also developed a special launch tower for us, which you might have seen before we started the talk, and I'll show you again, to carry this vehicle that we're developing up to about 120,000 feet. So hanging on the balloon is this 7,000-pound vehicle that has a rocket motor in it. And it's actually shaped to look like the Mars entry vehicle like you saw for MSL, that vehicle that Ian showed at the very beginning, entering the Martian atmosphere. We want that same shape to attach the SIAD to and the same shape in front of the parachute so we get the same aerodynamics. So we have this 4.7 meter, a little more than 15-foot diameter vehicle. And inside we have this Star 48 motor. It's a very large rocket motor. It's the same rocket motor, in fact, we've used in the past as the third stage on launch vehicles to get spacecraft to Mars. I worked on the Mars Exploration Rover mission. We used 2 Star 48s on that to get our 2 Mars Exploration Rovers to Mars in 2003. And so we have one of these motors in the vehicle, and attached to the vehicle on the side is the SIAD, and inside the vehicle is the parachute to be pulled out. So we take the vehicle up to about 120,000 feet on the balloon. That's as high as the balloon can go, so it drops off the vehicle right there. And at that point, very shortly, within a few tenths of a second after it being dropped from the vehicle, it fires some spin-up motors up, fires its big rocket motor, and accelerates from 120,000 feet to about 180 to 200,000 feet, going at about Mach 4. Once it's going to Mach 4, we can then deploy the SIAD. We then deploy this thing up here, which we haven't really talked much about, but we had to develop another technology just to test these technologies, which was a balloon. So this is another inflatable device. It's kind of like the SIAD-E that Ian talked about. It has ram air inlets, and it also operates at supersonic speeds, and it provides enough drag that it can pull the parachute out of the vehicle and deploy it. So we deploy this balloon at about Mach 2.7. That pulls the parachute out at Mach 2.5. And then we see both the parachute operate and the side operate. We have a ton of cameras on the vehicle, load sensors. We measure the trajectory very accurately of the vehicle with a GPS and inertial measurement unit and so on. All this data is then collected on the vehicle. The vehicle then comes down with some help from the parachute and then comes down into the ocean. This vehicle is actually designed to float. It has foam core in the composite structure to guarantee that it floats in the water. So this is our supersonic space boat that we fly out here, land in the water, and then we send boats out to go collect it and bring it back. So now I'll show you how that all goes. This is the special tower we had to develop. It turns out the way we normally launch balloons, or the way the Columbia Scientific Balloon Facility normally launches balloons, is they have a truck that drives around with a payload on it under the balloon until the balloon is about overhead, and then once they get it in the right place, they let go of the payload and the balloon takes it up. Because we had a big Star 48 rocket motor in here, that wasn't considered to be a safe thing to do, to drive a truck around under a big rocket motor. So we had to develop this tower so that we could launch it remotely. And so there's no people around here when we launch. And this allows the balloon, which is tracked way back here, about over here, to come up over the tower, take the vehicle off, and launch it. So this is a special launch tower that was used for the first time for our mission. This is where we're doing this is on the west end of Kauai. This is a facility there, for the Navy facility called the Pacific Missile Range Facility. They do lots of missile tests out there. They have combined tests with Vandenberg and with Kwajalein, where they're firing missiles at each other, trying to hit missiles together out over the Pacific Ocean. And so they're a fantastic facility, and also provided us with very unique weather conditions that we needed to be able to launch our balloon and to make sure that it took the Star 48 motor away from the populated areas. And we had to wait a little while, but we got the proper winds to give us that opportunity. So that was a fantastic facility on the west end of Kauai to do the operation from. So here we go. So they're setting up the vehicle. Our guys are really fast. They work very quickly. And so this is the balloon now filled up with the helium. It's actually, the balloon continues out here. This is just a little bubble at low altitude. Only this much of the balloon is filled up with the helium, but as it goes higher up, it completely fills up. The balloon stretches all the way out here to the tower. Here we have the guy filling up the balloon. There's a guy on each side holding a big pipe. that's actually pretty cold because it has expanding helium in it. The balloon is let go of the spool. This little collar here will come off so the entire balloon can fill with helium. We have a little recovery parachute here in case we have to abort the mission for some reason, which we did not have to do. This all was on June 28th, just this last summer that we did this launch. Here's our control room. And here you see the balloon now going up to altitude. As the balloon goes up to altitude, it fills up. You see our little vehicle down here. So you see it's a really big balloon.
Attention all stations. The test vehicle is go for drop. I repeat, test vehicle is go for drop.
So now we're at 120,000 feet. That took 2 hours. We just kind of skipped over that part.
2, 1, drop.
There's the vehicle dropping away from the balloon. So there's a camera on the balloon. And now the vehicle's falling. We fire spin-up motors to spin the vehicle up and stabilize it. And then we fire this big Star 48 rocket motor. That rocket motor fires for about 71 seconds and accelerates the vehicle from 0 to Mach 4 in that time. And also we're accelerating up out of the atmosphere. You can see the Earth in the background there. You can see the balloon that we just left behind us going by. We busted the balloon on the way out. In fact, the video will stop in a second here, and you can see the balloon very clearly. There's the balloon that carried us up. Got a nice big rip in it, so it went back down in the water exactly as we planned, and we recovered the balloon from the water because we have to be very environmentally conscious and clean up our mess. And so the vehicle is now spinning. The rocket motor is firing as it accelerates. As it goes up, you hear the motor firing, and it gets quieter and quieter as we get up because the atmosphere is getting thinner and thinner. Now the spin-down motors fire after the rocket motor slows down. So now we have a non-spinning vehicle. It's ready to test the technologies. So we're going to pop open a camera lid here that will see now we have a clear view of the side, and boom, that's how fast the side actually deploys. So it deployed perfectly. It is now going about 3,000 miles an hour. You can't really tell, but it's taken a pretty strong wind there and deployed beautifully into that wind and provided exactly the drag we expected. In fact, we had planned to do this test next year, and so we actually got this done a year early. This completely qualifies this technology, which is now really ready to use at Mars. Now here we are deploying the Balut, a 4.4 meter Balut, which comes out. Here it is in the high-speed video. We've got a lot of really nice high-speed, high-res video of all these devices working. So you see the Balut coming out and inflating. It now is generating the drag so it can get ready to pull the parachute out of its can. So now once we let go of this, we cut it loose, we pull the oh, look at that. We pull the parachute out and tested the parachute. So you saw the parachute actually got destroyed. I'll talk a little bit about that. That was actually a very good test for us. We're very happy to see that in a way. And now the vehicle is coming down, and now it's in the thick atmosphere of Earth. So this is deflated because it only had about 3 psi, and it's not coming down into the 14 psi Earth atmosphere, and then it lands in the water. So here we have a picture you can see the parachute in the water there after the boats get there to recover the vehicle. You can see the parachute underwater. It looks like a big jellyfish under the water. And now we have the guy sitting on our supersonic space boat waiting for the larger boat to come by. These are Navy ordnance divers. They come in and safe the vehicle, make sure it's safe, and help recover it. While they were sitting there waiting on the vehicle, they have little GoPro cameras, so we heard what they were saying. They said, you know, bro, there's no one I'd rather be stuck with in the middle of the Pacific Ocean on a sinking spaceship than you. Yeah, high five, fist bump. So then the big boat comes along. We pick the vehicle up out of the water, and we recovered the vehicle successfully. Also got the parachute out of the water. You see the SIAD on there. So we recovered everything we wanted to cover. This was a great success. The whole purpose of this flight, in fact, wasn't to test the parachute and the SIAD. The purpose of this flight was to show that this test vehicle could deliver the technologies to the proper conditions, that it could collect all the data, take all the pictures, and everything was a perfect success. So in fact, we were very lucky that we were able to get the SIAD and the parachute available in time to get them on the vehicle. Whether if we hadn't had them, we wouldn't have had them on the vehicle, but we did. And so we got an early test of the SIAD, which actually proved out the technology, and we got an early test of the parachute, which allowed us to see a parachute failure that now we're able to redesign the parachute and adjust for our real tests for the record, which are coming up this summer and next summer. And so those are the tests which we have to have the parachute and the SIAD succeed on. We're already done with the SIAD, but we're going to have them on there anyway to provide the proper environment for the parachute. And then we've redesigned the parachute to be able to take the loads that it's going to see in the supersonic flight. So our accomplishments, we flew the largest inflatable aerodynamic decelerator ever deployed and tested it at supersonic conditions. This was actually technology advancement on its own, even though it wasn't originally a part of our project scope. We developed this Balut, which was used to pull the parachute out. That thing worked beautifully as well. It was the first supersonic pilot deployment, so the first use of a pilot Balut to pull a supersonic parachute out. This may, in fact, be useful for future missions to use a Balut to pull out a parachute instead of what we've been doing in the past, which is a giant gunpowder-powered cannon, basically. But as these parachutes get bigger, the cannon gets bigger, the reaction loads are larger. So we may want to use a pilot balloon in our future missions. And as the largest supersonic parachute ever deployed, and you saw that it was a spectacular deployment, and an unprecedented quantity and quality of data. You saw some of the kind of the scratchy films of the earlier tests that Ian was showing you. We got beautiful, beautiful, high-resolution, high-speed videos from our machine vision cameras, as well as our GoPros that we had. Actually, literally commercial GoPros on there for taking some of the images. And it was just a fantastically successful mission. We got all the telemetry back. Well, since we recovered the vehicle, we were able to get all the memory cards out of the cameras and get that information. So we now have this test platform. We developed a new capability. This is a new wind tunnel. We now have a stratospheric Mach 4 wind tunnel that we can use to test these technologies, which is exactly what we're going to be doing this coming summer and next summer. So we're now building more vehicles. This is a picture from the high bay about a month ago. Here is vehicle number 2. And vehicle number 3. So vehicle number 2 is having the SIAD installed. We inflate, and actually this is a test of inflation of the SIAD. You see a bunch of camera targets out here, so we're testing cameras and making sure that we understand how the deflection of the SIAD can be measured by the cameras, and we're testing the leak rate of the SIAD in this test right here. Right now, in fact, the reason these ILC Dover guys are here is we're now actually installing a SIAD on this vehicle. In the same high bay. So we're now getting these 2 vehicles ready for future flights, and we're developing the parachutes. We're planning to do another rocket sled test of the parachutes. We have 2 parachute vendors developing parachutes now for our flights, for upcoming flights. We're going to be doing rocket sled tests this February, and in June we'll be flying these vehicles, and also possibly following June in 2016 to test the SIADs and parachutes, and finally prove them out so that they can be used on future Mars missions to land larger payloads at higher altitudes with more accuracy. So just to close, this is one of our favorite quotes from Theodore Roosevelt. Far better it is to dare mighty things, to win glorious triumphs, even though checkered by failure, than to rank with those timid spirits who neither enjoy nor suffer much because they live in the gray twilight that knows neither victory nor defeat. So we like taking risk. If we're not taking risk, if we're not pushing the envelope, if we're not having failures, then we're not doing the right thing in the technology program. That's our job. We are trying to improve the capability of these systems. We're trying to get the best performance we can out of them. We are taking risk to do that. And we are making sure that we're doing it cost effectively. We are developing technology for the next generation of Mars landers. So that's it. So if anybody have any questions? So if anybody has any questions, feel free to ask. Yeah.
So this, I mean, it's great that this test for this. There was some talk about you going to Venus and maybe using airships maybe for longer term exploration. Obviously, Venus kind of has the opposite problem. That its atmosphere is a lot denser. Is any of this technology going to be relevant? Is that been looked at for using for those missions at all too? Or?
Yeah, those missions are in a very, very early conceptual stage, so they're not at a point where they have to worry too much about exactly what technology they need. But yeah, what you said about Venus is right. It's a much thicker atmosphere, so it's much easier to slow down. You don't really need as supersonic capability at Venus because even a blunt body without a parachute or without a side will slow down to subsonic speeds, and then you can deploy a subsonic parachute to slow it down the rest of the way. So it's relatively easy. Those missions would actually go to the kind of the mid-atmosphere of Venus. They wouldn't go to the surface where the atmosphere is really thick. They'd go more to sort of this atmosphere and float at the cloud level for doing experiments at more Earth ambient environments. Yeah.
Yeah, I got 2 for you. Some years ago, I met a young lady who did a PhD thesis at Stanford on supersonic retropropulsion. And what she discovered is that if you stick a rocket in the middle of an aeroshell, it acts like an aero spike and actually decreases the drag. Yep. And she discovered if you space a few around the perimeter, well, not necessarily all the way out to the edge, but facing outward in just the right angles and just the right number of them, it increases the drag. So they're not used for propulsion, for retropropulsion, they're used for increasing the drag. Is this something that would be synergistic with what you're doing, or would it be orthogonal to it or harmful to it?
It's, my microphone on? You guys hear me okay? So the question was about, actually, yeah, it was at the microphone. I know that paper. I know the students, Noel Baekhyun at Stanford, so I'm very familiar. The areas of her research is something called supersonic retropropulsion. So, I spoke all about how important it is to develop drag. If you have an atmosphere in general, you want to use that atmosphere as much as possible to slow you down. As you get heavier and heavier, it may not be possible. You may not be able to build devices big enough to produce the drag you need, particularly at Mars. And so to solve that, you turn on your rocket engines that much earlier. That means a lot of fuel. Fuel weighs a lot. It weighs a lot more than nylon does. But if it's all we have, then that's what we're going to have to use. She was looking at, are there ways of using that fuel to create more drag? In general, to do that, you have to thrust it at moderately low levels. If you want to be the most fuel efficient, you're going to turn your engines on as fast as they can go, as hard as they can go, and slow down as fast as you can. To be able to use drag or have the fuel somehow augment the drag, you have to turn on the engines at a very low level. And so it ends up being not particularly fuel efficient to try to do that. You can increase your drag or your total deceleration force by about twice, but if you just turn your engines on full throttle, you can increase your deceleration force by about 10 times. So it tends not to be the most mass efficient to try to do that. It's still very worthwhile technology, and it's something that NASA is looking at very heavily in parallel with some of these supersonic decelerator devices.
Yeah, thanks. Do you plan to use something like the sky crane at the end of the trajectory to lower the machine onto the surface?
Certainly for the near term, there's a 2020 mission coming up to land another very large rover on the surface of Mars, and we will use the sky crane for that. The extensibility of the sky crane, we think we can go somewhat larger. It still remains to be seen if that's the most efficient, most practical way to land 40-ton payloads on the surface of Mars. It may be more useful just to keep the engines on the vehicle that lands on the surface rather than have the sky crane.
Well, for the MSL, the sky crane just flew away and crashed. It would seem reasonable to put some instruments and solar panels on it and have it land gently and sending back data for years.
We could end up doing that. That's certainly a possibility.
Yeah, thank you.
Hello. Is there a vast concern with robotical or orbital concern here where there's a drop in altitude when you send up the vehicle?
I'm not sure I caught the question. So, I mean, what are you...
I'm kind of wavering here. When the vehicle goes up, there is a drop in altitude that could be orbital decay, whereby there has to be a boost, like with the ISS. There's a boost to keep the altitude up.
Ah, okay.
Orbital decay.
Yeah.
So spacecraft that are in orbit around another planet, even at the very high altitudes that they're in orbit, sometimes there's a very, very little amount of atmosphere. And that atmosphere over time slows them down. And so eventually we have to accelerate them or boost them to higher altitudes to get them back to the orbit that we want them at. The spacecraft, the things that we're dealing with, aren't things that we're going to be putting in orbit. We're going to take them all the way to the surface, and we're going to put them on the ground. So they're not moving, they're not in orbit, they are on the ground, like you and I are standing on the ground today.
I've heard about a certain secret that we don't talk about, that the International Space Station isn't actually in space. It's in the very high upper atmosphere of Earth, and so it does get slowed down a little bit, and we have to speed it back up every once in a while.
Thank you.
Sure.
Can you get the microphone? Thank you.
Is this the only thing that NASA is working on to get equipment or people onto Mars, or do you guys have, is this like one of 10 projects that NASA has going on?
This is probably, I mean, it's going to be very difficult to get people on Mars. As Ian said, we've put a 1-ton thing on Mars. If you want to put people on Mars with their 2-story condominium and a rocket to get them back, it turns out they want to get back. You need to put 20 tons to 40 tons on Mars. So that's 20 to 40 times as much as we've done. And so it's going to take a lot of steps to get there. You can't just all of a sudden leap to 20 to 40 tons. And so we're probably the second step of a 12-step program to get to the, of course, the first step is acknowledging you have a problem. To a 12-step program to get to actually landing people on Mars. So it is going to be a big deal. So there are developments right now going on for something called a HIAD, a hypersonic inflatable aerodynamic decelerator. which is designed to slow the vehicle down on entering the atmosphere. So it's that heat shield that you saw with all the flames coming off of it. We could make a big inflatable one of those potentially and have a larger vehicle with a lower ballistic coefficient to slow down more at Mars. As was mentioned before, we're looking at supersonic retropropulsion, which is another way of slowing the vehicle down. It takes more fuel, but it's a little bit simpler and more straightforward. It can reduce the drag of the vehicle, but you get a lot of thrust to slow yourself down. There are many other technologies for mid-LRD vehicles, for guidance through the Mars atmosphere, for various phases of the mission, different heat shield materials, to try and get humans down on Mars. It's going to be a big program, a big development program to get to the point where we can put humans on Mars. It's not a trivial thing, but we're going to develop a lot of new technologies that will probably have other applications just to do that difficult job. Anything else on that, Ian?
That's good.
Yeah.
My understanding is that you use the aerobraking, at least with the MSL, the existing missions, you use the aerobraking for all your slowing down, right? You don't do any retro rocket when you reach Mars at all?
Not all the way. Like what we showed in the MSL video, you can only use the atmosphere so much. So MSL, for example, the parachute got it down to about 200 miles an hour. And then we had to turn on our rockets at 200 miles an hour to take out the rest of that velocity, the rest of that energy, and bring it to a zero velocity and on the surface.
But no rocket before you hit the atmosphere.
Right. Usually.
Usually.
Yeah.
Yeah.
I mean, just an example, just to be precise, the Viking landers actually went into orbit around Mars before they entered. And so in that sense, you can say they used rockets to slow down at Mars before they entered. For all of our other missions, for Pathfinder, Mars Exploration Rover, Curiosity, Phoenix, they entered the atmosphere directly from their trajectory from the Earth, so they used no rockets at all to slow them down. They just hit the atmosphere, boom, as fast as they could.
So my question is, I saw this paper about a new way of getting to Mars called ballistic capture. And the idea was that you would do a real fancy little dance, and you would minimize the delta V that you had to remove at the planet. Is that a significant savings, or would that be negligible?
Not for our landers. That's actually a very important savings for orbiters. So if you want to go into orbit around Mars, you have to fire a rocket to slow yourself down and capture into orbit around Mars. These techniques, using these instabilities, really, sort of high order instabilities in the orbits around the sun, allows you to slow the vehicle down without using rockets. So you can reduce what may have been a 2 kilometer per second rocket firing to slow you down to get into Mars orbit to maybe 1.5 kilometers per second. That's a lot of fuel. So that can help you a lot. But when you're coming in with a lander, you've got the atmosphere to slow you down, so you don't really need those rockets. But for missions like Mars Sample Return, where you want to get rocks back from Mars, or astronauts want to get back, they're going to need an orbiter around Mars to take them back. And so those techniques may be important for getting things into orbit around Mars for the return trip.
Thank you.
The internet. The interwebs. Let's see what we got here. Key 40H. I don't know if that's like
It's a ham radio call sign.
Ham radio?
KE4OH.
KE4OH. This is KE4OH. Asks, Mark, Ian, what landing tech would you make with an infinite budget? Thank you for the infinite budget. We've been waiting for that.
Cushions of money to land software.
Yeah, we just had to layer the ground with $100 bills.
Yeah.
Actually, that's a very interesting question, because if we had an infinite money, we might not develop as much new technology. If you have a lot of money, you can afford a big launch vehicle, and lots of them. And so you may say, oh, well, let's just kill the problem with a big launch vehicle, a lot of mass, and just use big rockets to slow the thing down. Forget the parachutes, forget all that. Just put a lot of fuel on, have these ginormous rockets that cost $10 billion a pop, and go that way. But we don't have an infinite budget. And so that's one of the reasons we developed these technologies, is because they allow us to do things cheaper, more cost effectively. We can have a smaller rocket which uses the atmosphere to slow us down instead of big rockets, trying to take as much advantage. The nylon and the Kevlar and the Technora will always win against the propellant or the fuel that you would need in terms of mass. So that makes the things cheaper. So if we had an infinite budget, we might not develop as much technology. But given the limited budgets we have, it turns out it's more cost effective to spend money on developing these technologies to allow you to reduce the cost of the mission overall. So I don't know if that answers the question for KE4OH, but that's my answer. You want to take this here?
Vandellis Wild asks, will inflatable decelerators be developed for long cylindrical structures, parenthetical rocket tanks, for example? The kinds of devices that we're developing, the inflatable structures, are generally built around the blunt body aeroshell designs that we've used to land on Mars, designs that have very high drag coefficients. As you get to larger and larger payloads, eventually you need to be able to stack those inside of launch vehicles. Launch vehicles tend to be very cylindrical objects. The payload fairings tend to be very cylindrical. So it's highly possible that the payloads of the future will be giant cylinders, and we'll have to inflate large devices around those cylinders to decelerate them very safely. So Vandellis, absolutely, that's a possibility. Any other questions? Thank you all for coming.
All right, thanks a lot.